Hello again, it's Randy, and we are to solve another machine problem. So this time it involves linear and nonlinear regression. So here's the instructions. 1. We need to write a MATLAB script to solve the problem using the following. So using linearization of nonlinear relationships and using the fit function that we learned in MATLAB Academy. So the problem is in Andrade's equation where it is an empirical model that relates temperature with viscosity. So we have mu, which is our viscosity, and equal to d times e raised to b over the absolute temperature. So mu is the dynamic viscosity of water with the units 10 raised to negative 3 Newton second per meter squared, and Ta is the absolute temperature K, and both B and D are some unknown constants. We need to fit the model to the following data for water. So we have the following data, an increasing temperature that reduces the viscosity of the water. So we need to also predict the value of mu if the temperature is negative 10 degrees Celsius or 263 Kelvin. Okay, so we can work with that. Let's go on to MATLAB. Okay, so first order of business, we need to CLC and clear for any previous variables, and I want to do format long. And then we are gonna input our values, our given values. So we have t. For this one, we are gonna add 273 to our default values right here, since I want to turn them into Kelvin instead of temperature. So let's go ahead and do that. We're gonna have 273, 278, 283, 283, 303, and then we're gonna make them into column. Next, we're gonna have our mu, our dynamic viscosity, and if you notice here, we have 10 to the negative 3, so I'm gonna multiply them to 10 to the negative 3. So we're gonna have and then what we're gonna do next is we're gonna plot this. So plot t mu, and I'm gonna want let's say blue circles. So let's go ahead and run that, see if it works. And there you go, that's our data for now. And then next we're gonna get our values using the fit function. So I'm gonna have f1 and goodness of fit 1, since we're gonna be using this twice, and then fit t against mu. Since we have an exponential function, I'm gonna be using exp1 instead of poly1. Okay, so we're gonna run that, and there you go. So it follows the general model that we have right now, and then we have our coefficients, which is 2.316 and negative 0.02634. And then our r-square is actually already pretty high, it's 0.99. So let's go ahead and plot the fit line that the fit function gave to us. So we're gonna hold on to that. I'm gonna turn on the box, and then gonna turn on the grid. So plot our f1, t and mu, and then I want circular blue markers. Let's go ahead and run that. Okay, so right now this is our best fit line that the fit function gave to us. It's actually pretty good for now. So next we're gonna linearize this, but before that we're gonna put some labels and a title for this one. Okay, so next we're gonna temperature input, then variable, dynamic viscosity of water. Then we're gonna hold that off. Then next we are gonna linearize this data. So since we have this kind of data, the way we're gonna linearize this is we're gonna take mu and multiply it with the natural logarithm, since we have e here. So t is just gonna become 1 over t. So let's put that in. Our x value is just going to be equal to 1 over t. Gonna omit that. And then y equals logarithmic value of mu. I'm also going to omit that. We're going to put in a figure handle because we're going to convert this into a .m file pretty soon. Then we're going to scatter. Oh, and then let's see how that looks. Okay, so this is our new linearized data. It looks much nicer, and of course it's not going down, so we can clearly see a relationship between these two values. Okay, so next we are gonna put a title first. Right here, and we it, then we box. X label, RT, and then y label, ln of mu. Okay, so now we're gonna want to use our fit function to find the coefficients for this particular equation. So we're gonna go ahead and do that. We're gonna have f2 and goodness of fit2 equal to fit x and y. And then for this one, we're gonna start using poly 1 since the equation is now in the form of y equals mx plus b. So we're gonna put a figure handle there, and we're gonna plot f2 with y and then blue circular markers. Let's go ahead and run that. Uh-huh. Uh-huh. And there you go. That's our fitted curve right there. It looks much better. And then as you can see, our R square actually got pretty higher compared to before. So we now have 998 instead of 993. Now we're just gonna put some labels on there, turn on the grid, turn on the box. Then we're gonna put in the title. Line. Next, we're gonna use X label. Of course, this will be the same. And then we're gonna run that to see if it looks pretty nice. Okay, so that looks much better. And now, of course, we're gonna determine the coefficients D and B. So determine coefficients. So we're gonna have our intercept, which is equal to f2.p1, as you can see from here. And then our b is actually just equal to the intercept. Next, we're gonna have our slope equal to f2.p2, and then our d is actually the exponential of the slope. I'm gonna want to omit this since we already know those values. Maybe except for d, we're gonna see. Okay, so the value for d is actually pretty low with a -7 exponent. So we're gonna omit that now. Then next, what we're gonna do is actually plot the nonlinear regression line. So we're gonna put in another figure handle, and we're gonna plot t against mu again with blue circular markers. Hold on, box on, and then turn on our grid. Actually, let's just copy this. And then for this one, we're gonna have to use tfit, and then use linspace to create an array of datas for our temperature values. And then it's gonna have 100 different values from T1 to the end of the temperature values. And then we're finally going to use mu fit, our actual equation, and then we're going to multiply them. T fit, there you go. But let's see first if it works. Gonna run that. Okay, so it seems like it's working. Okay, and there's our values for mu fit. So next, I want to put in a certain x limit, let's say 260 to 315. And then finally, we're going to predict the viscosity at a certain temperature. So we're going to T predict. Oh, I sorry. I forgot to plot the best fit line for this one. So we're going to do just that. T fit against mu fit. And then a red line. Okay, so there you go. This is our new best fit line, which looks pretty nicer compared to the ones that we had before. This one has a bit of a gap over here, and this here too. And this one has a much smaller gap in between the values. Next, what we're gonna do is predict the value. So we have 273 minus 10 because our temperature that we want to predict is at negative 10 degrees Celsius, and then mu predict. I'm gonna use the same equation, but this time we're gonna be replacing T fit with T predict. We're gonna omit both of those and then hold on and then scatter and the T predict against the mu predict with, let's say, a circular green marker. Then we're gonna hold that off. So now we need to display that. So as you can see, this here is our predicted value. Finally, we're going to display what our mu value is at a certain temperature T. So we're going to have at T equal to something. So we're going to use num2 string. The value of mu is mu predict, and we put up. So let's run that. Okay, so there is our center temperature and the value of mu. So I think we've pretty much solved this machine problem already. Thank you guys for watching, and I'll see you again next time if the opportunity comes to rise. See ya!